Weak topology. Weak topology. Got it. Okay. We are discussing about weak topology. Number 3. Right? Today we are discussing about weak topology. So unit 3. Unit 3. Weak topology. Share screen. Share screen. Whiteboard. Okay. Today we are discussing about unit 3. Right? Unit 3. Weak topology. Topology and star weak topology. Weak topology. Star weak topology. Star weak topology. So we'll define first. In this chapter, what we are discussing about definition. Definition of weak topology and star weak topology. Star weak topology. This one. Definition. So we introduced the topology. So in this one, what we are discussing first, definition of weak topology and star weak topology. And most important, we prove a well-known theorems. These are vital theorems. We are discussing about those theorems. What is that? Naglu theorem and Jordan van Neumann theorem and Squash inequality and Rees representation theorem in Hilbert space. Already in the first chapter, normal linear space, we discussed about Rees representation theorem. Rees representation theorem in normal linear space. Here, Rees representation theorem for Hilbert spaces. So Hilbert spaces. First, we introduce topology. We introduce topology. We introduce topology. Topology of N. Of capital N. N means what? Normal linear space. No, N, which will be called weak topology. Which will be called weak topology. Weak topology will be called weak topology on N. N. Which topology? Select text. Okay. Weak topology on N. Determined by N star. Determined by N star. So what is the difference here? N is a N means here weak topology. Weak topology. Weak topology. N star is the N star means the weak star. Weak topology. Weak topology. So weak topology. So this is nothing but conjugate of N. Conjugate means you already lesson in complex numbers. Complex numbers Z equal to A plus IB. Its conjugate Z bar denoted by Z bar means here weak star. Z bar is A minus IB. Here conjugate each other. So no clear. So we know that N star. So we know that I'm adjusting whiteboard. So, no? So we know that N star equal to that N star. Now that N star equal to F by F. F N tends to complex. N tends to complex. C is continuous and linear. Is CTS. CTS means continuous, linear, linear. So let small a belongs to capital N. Let small a belongs to capital N. Small a belongs to capital N. Small a belongs to capital N. And F1, comma, F2, comma, so on, Fn belongs to N star. N star and epsilon greater than 0. Epsilon is greater than 0. Define the subset U. Define the subset U. Define the subset U of N as follows. N as follows. Of N as follows. So U equal to A comma F1 comma F2 so on Fn such that epsilon that equal to within the set symbol X belongs to capital N. Modulus of supremum of I. Supremum of I. Fi of X minus Fi of A. So close this. In this two, what we will get? Limit X tends to N. Modulus supremum of I. Within the bracket, we are taking Fi common. Within the bracket, X minus A. So which is less than epsilon. Here also which is less than epsilon. So U equal to U of A comma F1 comma F2 so on Fn. That's that epsilon. A neighborhood of is NBD means neighborhood of A. Neighborhood of A. So what weak topology? Weak star topology. Next what I said, we need to go to theorem. Theorem ALAGLU, ALAO GLU 3.3.12. 3.3.12. 3.3.12. ALAGLU theorem ALAGLU. Theorem ALAGLU ALAO GLU. ALAGLU. So ALAGLU is the scientist, mathematician. So he introduces the theorem. A statement. What is the statement? If n is a normal linear space, then the closed units PR S star, F belongs to n star, such that norm of F less than or equal to 1 in n star is a compact Hausdorff space in the weak star topology J n star n. So here, so if statement I'm writing, if n is a normal linear space, I'm writing NLS normal linear space, yes, then the closed units PR, then the closed units PR, closed units PR, S star, S star that equal to F belongs to capital N star, such that norm of F less than or equal to 1 in n star is a compact Hausdorff space, HAUSDORF Hausdorff space in the weak star topology see J n star comma n star comma n. So proof of this theorem. So since J n star comma n is Hausdorff on n star, is Hausdorff on n star. Hence in particular it is Hausdorff on a star. Hausdorff in S star. Hausdorff in a star is a Hausdorff. Hausdorff is a Hausdorff. Is a Hausdorff. So now let us prove that required to prove S star is a compact weak. RTP means required to prove S star is compact in weak star topology. Weak star topology. So define D of X for each X belongs to N. And D as follows. D as follows. D as follows. D equal to capital D. D equal to P. X belongs to N. X belongs to N. D of X. D of X. D of X equal to Z belongs to complex. Z belongs to complex C. C is such that mod Z less than or equal to norm of X. Less than or equal to norm of X. Where P stands for product. P means product here. Product here. So F belongs to D. It is equivalent to Fn tends to C. F belongs to D. Now it is equivalent to, it implies F of N tends to C complex. Right? Now clear the board. So Fn. So F of X belongs to D of X. F of X. F of X. So F of X belongs to D of X. D of X for all X belongs to N. X belongs to N. That is, F of X is less than or equal to norm of X. That means F of X means mod F of X is less than or equal to norm of X. So in other words, we may say S star is subset of D. Subset of D. Dx is a closed, here, Dx is a closed, here, Dx is a closed and bounded subset of D, and bounded subset of D, bounded subset of D. And hence by Tikhonov's theorem, and hence by Tikhonov's theorem, Ty CH2 NO FF is Tikhonov's theorem. By Tikhonov's theorem. D is compact. D is compact. Since S star is subset or equal to D. D is a compact. It is sufficient to prove that S star is closed. D is compact. D is compact. It is sufficient to prove that, it means prove that S star is closed. Star is closed subset of D. Subset of D. Star is closed subset of D. Star is closed subset of D. Closed subset of D. Closed subset of D. To claim S star is compact. To claim S star is compact. Okay. However, it is easy to see that the weak star topology on a star is equal to the weak star topology. Weak star topology is equal to product topology on a star. Product topology on S star. Product topology on a star. A star regarded a subspace of D. What is a star? A star is regarded subspace of D. Subspace of D. The S star will be compact and S star is closed. S star is compact and S star is closed. S star is closed. In the weak star topology, weak star topology. Weak star topology. So let F be the weak star closure of S. Let F be the weak star closure of S. Weak star closure of S star. Weak star closure. Then by definition of limit point, limit point, then definition of limit point, x comma y belongs to capital N and epsilon is greater than 0. The open set V, open set V, open set open set V. 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 Here V of F comma x comma y comma x plus y comma epsilon must contain some G belongs to S star. Must contain some G belongs to S star. So, however, we have to clear them. Okay. Next. So now modulus of g of x minus f of x is less than epsilon g of x and f of x. G of x and f of x. G of x, here modulus g of x minus f of x less than epsilon, comma, mod g of y minus f of y less than epsilon, comma, mod g of x plus y, g of x plus y minus f of x plus y, x plus y. Here minus given, printing mistake. So we need to write x plus y less than epsilon. These three conditions we'll use in the further. So since G belongs to S star, G belongs to S star, we have G of x, norm G of less than or equal to 1. It follows that f of x, yeah, f of x less than epsilon plus g of x, mod g of x less than epsilon plus norm of g, norm of x less than epsilon plus norm of x, norm of x. So yeah, epsilon is arbitrary. Epsilon is arbitrary. Epsilon is arbitrary. We have f of mod f of x less than or equal to norm of x and norm of f less than or equal to 1. So G is linear, we have. So G is linear. We have G is linear, we have. G is linear. We have means G of x plus y. Participants can G of x plus y. It can be written as G of x plus G of y. G of x plus y can be written as G of y. Now, mod f of x plus y minus f of x minus f of y modulus that equal to modulus f of x plus y, f of x plus y minus g of x plus y plus g of x minus f of x plus g of y minus f of y, f of y modulus plus is less than or equal to, f of modulus of f of x plus y minus g of x plus y, g of x plus y modulus plus g of x minus f of x plus mod g of y minus f of y minus f of y. That less than epsilon plus epsilon plus epsilon that equal less than 3 epsilon. So what we did? So f of x plus y equal to f of x plus f of y. So this completes the proof of the theorem, Angular theorem. This is complete. This is the complete proof of. This completes the proof of theorem. Okay. Now clear the board. Next, Hilbert spaces 3.4. What is Hilbert spaces? Previously in the first chapter, normal linear space, we discussed it. Hilbert space is complete inner product space is called Hilbert space. Complete inner product space is called Hilbert space. 3.4 Hilbert spaces. Hilbert space. What I said? Definition: a complete inner product space. Inner product space is called Hilbert space. Hilbert space. So now we'll discuss inner product space. So there's properties. Inner product space or inner product space denoted by capital I. So by short form IPS means inner product space. So denoted by within the common bracket small comma, denoted by this one that. So is a complex linear space together an inner product. Is a complex linear space with inner product. V cross V is a complex C. That found symbol, by mistake found symbol came in the textbook. So that is C. Such that C means complex. Here such that ST. So what is the first property? X comma inner product. We have to read as inner product X comma Y. Simply don't treat it simply X comma Y. Inner product of X comma Y can be written as inner product of Y comma X whole bar. What is that whole bar? Whole bar means suppose in complex number Z equal to A plus IB. Z bar what we'll write? A minus IB. That is the means A minus IB is the conjugate of A plus IB. A plus IB is also conjugate of A minus IB. Here Y bar Y comma X is conjugate of Y bar of X. X comma Y comma X conjugate is Y comma X bar. Second property. What is second property? AX plus BY comma Z that equal to A into X comma Z. We have to read as inner product of X comma Z plus B into inner product of X comma Y comma Z. This is Y comma Z. Right. So what is third property? What is third property? X comma X. X comma X is greater than or equal to 0. Inner product of X comma X equal to 0. If and only if means also known as by implication. If and only if X equal to 0. Using first and second property, we will raise third property also. What is that? X comma A, X comma AY plus BZ. AY plus BZ. That equal to A bar is outside X comma Y, inner product of X comma Y plus B bar outside inner product of X comma Z. For x comma y comma z belongs to V. V means IPS. IPS means inner product space. Here A comma B belongs to complex. A comma B belongs to complex C. C cross. C will capital C. So now clear the board. Next, using these properties, we have to prove that 3.4.1 theorem, Jordan Van Neumann theorem. Jordan Van Neumann theorem. Is it 3.4.1 theorem. Jordan Van Neumann. The statement. I'm reading statement and you have to observe here. Let N be a normal linear space with the norm. Then there exists an inner product on N such that x comma x equal to norm x whole square for all x belongs to N, if and only if the norm satisfies the parallelogram law. What is the parallelogram law? Norm of x plus y whole square plus norm of x minus y whole square equal to twice norm x square plus norm y square x comma y. What is this connectivity of this theorem? Yeah, in the lower classes, we have to read already. A plus b the whole square plus a minus b whole square equal to twice a square plus b square. Nothing but this is only. So in norm properties, inner products, we are using, you have to prove that this is a parallelogram law. So statement, let N be normal linear space. Let N be normal NLS, normal linear space with the norm. Then there exists inner product. Then there exists inner product on N such that x comma x that equal to norm x whole square for all x belongs to capital N. X belongs to capital N. If and only if norm satisfies the following. If and only if norm satisfies the parallelogram law. What is that parallelogram law? Norm of x plus y whole square plus norm of x minus y whole square equal to twice norm of x whole square plus norm of y whole square. So proof. So proof. Let inner product on N such that x comma x equal to norm x whole square. For all x belongs to N. For all x belongs to N. Then we have norm of x plus y whole square plus norm of x minus y whole square equal to, this is norm we are writing in an inner product. inner product form. What we'll write? So x plus y, inner product of x plus y, comma x plus y, plus inner product of x minus y, comma x minus y. So this we need to expand. How you will expand? First, x comma inner product of x comma x. Nothing but multiplication type. X comma inner product of x comma x plus inner product of x comma y plus inner product of y comma x plus inner product of y comma y. Plus first one is the second one, inner product of x comma x minus inner product of x comma y minus inner product of y comma x plus inner product of y comma y. Here observe my inner product of minus x comma y. Inner product of plus x comma y cancel. Inner product of minus y comma x plus y comma x. Here, so inner product of x comma x can be written as norm of x whole square plus inner product of y comma y can be written as norm y square plus inner product of x comma x can be written as norm x whole square plus inner product of y comma y can be written as norm y whole square. Here observe norm x square plus norm x square can be written as 2 norm x square plus norm y square plus norm y square can be written as 2 of norm y whole square. So in these two, we'll take common 2. Inside what will come? Norm of x whole square plus norm of y whole square. So this is the parallelogram law. Parallelogram law for all this, for all x comma y belongs to capital N. So now clear the board. So conversely assume that, conversely assume that norm satisfies the parallelogram law. Norm satisfies the parallelogram law. Norm satisfies the parallelogram law. Define the function. Here, define the function norm such that n cross n tends to complex as follows. So x comma y, inner product of x comma y equal to 1 by 4 norm x plus y, norm x plus y whole square minus norm x minus y whole square plus I norm x plus I y whole square minus I norm x minus I y whole square. So let us verify the axioms of inner product. Similarly, let us verify the axioms of inner product, IPS, inner product space. What are the axioms? Just now we discussed about inner product spaces. What is the first product? Inner product of x comma y equal to conjugate of y comma x. Yes, that property. Next, second one is inner product of x comma x. Inner product of x comma x equal to 0 if and only if x equal to 0. That is nothing but and another property. What is that? Ax. Third property, third axiom, ax plus by comma z. What we wrote, a is the constant scalar. We took outside a inner product of x comma z plus b into inner product of y comma z. So these three are the main properties. So fourth properties, we are using first and second property. We only derive the properties, right? So similarly, we can hence proved. Similarly, we can verify the all properties. Hence proved. Hence proved. So next, here what is coming? Case 2, alpha is a rational number. Alpha is a negative integer. Alpha is a negative integer. So 0 comma y. And alpha is a rational number. So what is that? Squash inequality, most important. Squash inequality theorem is most important theorem. Let V be inner product spaces. 3.4.2 theorem. Squash inequality, SCH WEA R TZ inequality. Squash inequality. What is most important theorem for squash inequality? Squash inequality is most important. These four named theorems, these four are most important. Only compulsory one question in the examination. So let V be a inner product space. Statement. Let V be a inner product space. So the inner product for x belongs to V. Let norm x equal to x comma x whole power 1 by 2. Then modulus of x comma y less than or equal to norm x, norm y for x comma y belongs to V. Let statement I am writing. Let V be the inner product space. Means IPS means inner product. Short term rating IPS inner product space with inner product. With inner product for x belongs to V. Let norm of x that equal to x comma x whole power 1 by 2. Then modulus of inner product x comma y. What? Inner product less than or equal to norm x, norm y. For x comma y belongs to V. For x comma y belongs to V. Proof of this theorem. Let x comma y belongs to V. Let x comma y belongs to V. X comma y belongs to. If y equal to 0, the inequality follows trivially. The inequality follows trivially. RIVILLY trivially. Inequality. So assume that y is not equal to 0. Assume that y is not equal to 0. Then norm y is greater than 0. Required inequality can be written as, so the inequality can be written as inequality can be written as mod of inner product x comma y by norm x is less than or equal to norm x. Less than or equal to norm x. This inequality, it is enough to show that norm y equal to, it is enough to show that norm y equal to 1. Norm y equal to 1. Norm y equal to. Then modulus of inner product of x comma y less than or equal to norm x. Okay, next. Zero less than or equal to, that equal to, here clear the board. So 0, here 0 less than or equal to norm of x minus inner product of x comma y whole square into y whole square can be written as inner product of x minus x comma y, inner product of x comma y into y, comma x minus inner product of x comma y into y. This can be written as x comma x minus inner product of x comma y minus inner product of x comma y into inner product of y comma x minus x comma y into y. This can be written as inner product of x comma x minus inner product of x comma y whole bar into x comma y minus nothing but whole bar is the conjugate. So a plus ib, a minus ib is the conjugate a plus ib into a minus b. What we'll get? Real part we'll get. Next step we'll get real part only. Conjugate is nothing but complex now. Complex conjugate. X comma y is the a plus ib consider. X comma y whole minus x plus iy, this we consider. X minus iy is the bar, nothing minus x comma y into y comma inner product of y comma x plus x comma y mod inner product of x comma y whole square into norm y whole square. Here norm y equal to 1. Next step. So norm inner product of x comma x we can write it as norm x whole square. Norm x whole square minus 2 x comma y into x comma y whole bar plus x comma y mod inner product of x comma y whole square is norm y whole square. Here what we need to know, norm y norm of y whole square equal to 1 here. We are using this condition in this one. What we'll get here? That equal to, so these are all equal, 0 equal to 1 equal 0, 0, 0, 0. That means norm x whole square minus 2 into modulus of x, inner product of x comma y whole square plus mod inner product of x comma y whole square. Nothing but this is minus 2 plus 1 is minus 1. No? So 0 equal to norm x whole square minus modulus of x comma y. No, that's fine. So transpose that side. You will get modulus of inner product of inner product of x comma y is equal to, is less than or equal to norm x whole square. Norm x whole square. This completes the proof. This completes the proof. Okay. This quasi inequality is the most important theorem. This completes the proof of this equation. Completes the proof of theorem. This completes the proof. That's enough. Now clear the board. So most important, another theorem is what I said, Reed's representation theorem for Hilbert spaces. What I said, Reed's representation theorem for Hilbert. Already in the first chapter we discussed. In the first chapter we discussed the Reed's representation. That is normal linear spaces. Normal linear space. This is normal linear space. So 3.4.8 Reed's representation theorem for Hilbert spaces. 3.4.8 Reed's representation theorem. RAESZ representation theorem. Reed's theorem for Hilbert spaces. Hilbert spaces. For Hilbert spaces. Reed's representation theorem for Hilbert spaces. So statement. If f is continuous linear functional, f is continuous means CTS consider. Continuous linear functional on Hilbert spaces. Linear functional on Hilbert spaces. Hilbert spaces on Hilbert spaces. Space H. Then there exists unique vector. Then there exists unique vector. There exists unique vector. Y belongs to H. Y belongs to H. Such that f of x that equal to f of x that equal to f of x comma y for all x belongs to H. So this two parts we can prove that uniqueness and existence. First we'll prove by uniqueness. Uniqueness proof. uniqueness, UNIQUENESS, uniqueness. Suppose there exist two vectors. Suppose there exists two vectors y1 comma y2 in H such that f of x equal to x comma y1 that equal to x comma y2 for all x belongs to capital H. What is H here? H is nothing but Hilbert space. Hilbert space. Hilbert space. So there is a. So then we have. X comma y1 minus y2 that equal to 0 for all x belongs to H. What is that? It is representation 3.4.8 theorem. It is representation. If f is a continuous linear functional on Hilbert space H, then there exists a unique vector y belongs to H such that f of x equal to x comma y for all x belongs to H. X belongs to H. So in particular taking x equal to y1 minus y2 y1 x equal to y1 comma y2. That means inner product of y1 minus y2 comma y1 minus y2 that equal to 0. This implies y1 minus y2 equal to 0. That means that is y1 equal to y2. y1 equal to y2. This is uniqueness. What is there first? So 3.4.8 theorem. It is representation. If f is a continuous linear functional on a Hilbert space H, then there exists unique vector y. Then the unique vector. If is a continuous linear function on Hilbert space, then there exists a unique vector y belongs to H such that f of x equal to x comma y for all x belongs to H. Proof. This we are proving two parts, uniqueness and existence. First, we are taking uniqueness. Suppose there exist two vectors. What we took y1 comma y2 in Hilbert space such that f of x equal to x comma y1 that equal to x comma y2 for all x belongs to H Hilbert space. Then we have x comma y1 minus y2 equal to 0 for all x belongs to H. In particular, taking x equal to y1 minus y2. So the inner product of y1 minus y2. So the inner product of y1 minus y2 comma y1 minus y2. So this implies y1 minus y2 equal to 0. So y1 equal to y2. So uniqueness. So now clear the board. Now, you need to take existence. Existence. Second part is existence. 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 If f equal to 0, then we can always choose y equal to 0. If f equal to 0, then we always choose y equal to 0. Y equal to 0. Which satisfies f of x equal to x comma y that equal to 0 for all x belongs to h, means Hilbert space. So let us assume that. So let us assume that. Let us assume that f is non-zero functional. F is non-zero functional. F is non-zero functional. The null space n null space n of f is a closed linear subspace. Closed linear subspace. Closed linear subspace of H. Therefore, n equal to n perp. This symbol is known as n equal to n perp. Perp means perpendicular. That this symbol I have written here. Perpendicular. So n means n perp. Since n is not equal to h. Necessarily n perp is not equal to 0. Necessarily. N perp is not equal to 0. Choose Z belongs to n perp. Z belongs to n perp. Z belongs to n perp. So Z is not equal to 0. Then Z does not belongs to n. Then Z does not belongs to n. From this it follows f of z is not equal to 0. From this it follows f of z is not equal to 0. Then for any x belongs to h, the vector f of z to x minus z into f of x is clearly annihilated, means totally destroyed, is clearly annihilated, annihilated by F. That is x f of z, x f of z to x minus z f of x belongs to capital N. So now clear the board. So since Z belongs to N perp, it follows 0 equal to x f of z into x minus z f of x into z. That is f of z inner product of x comma z, that equal to f of x inner product of z comma z for all x belongs to Hilbert space. Thus f of z that equal to f of z into inner product of x comma z whole divided by inner product of z comma z, that equal to inner product of x comma f of z into z whole bar whole divided by norm z whole square. Now the vector y. Now the vector y that equal to f of z whole bar whole divided by norm of z whole square into z meets the requirement of the theorem. This completes the proof. This completes the proof. So, friends, what we discussed today, Unit 3, weak topology and weak star topology. Now I will clear the board. Weak topology. weak topology. Weakened. Now, what we discussed in Unit 3. No, not what we discussed in Unit 3. It's the weakened weak star topology. No? First, we discussed about definition, weak star and weak star topology, and also 4 important, most vital theorems. What is those theorems? Squares inequality, and Anaglu's theorem, and squares inequality and Anaglu's theorem, and a ridge representation. Already in the first unit, normal linear space, we discussed about ridge representation theorem for normal linear spaces. Here, ridge representation theorem for Hilbert spaces. So, we are discussed, and also we discussed 4 most important theorems. For example, and also we used first we discussed about inner product spaces. Inner products is properties. That properties we used in squares inequality, and those are most important. These 4 theorems are most important. That is the Unit 3 life. Okay. Okay. Thank you very much. Thank you for giving me.